Welcome back to ECE 320A. Hopefully you have made it successfully through your first half of a week in your first week of the fall semester. In terms of announcements, you hopefully are working on your passport. You need to be reading Chapter 10, getting ready to do homework assignment number 1, which you can thank me, that was going to be due a week from today. I've switched it to a week from Tuesday when we come back. So we'll come back to class on Tuesday, and your homework assignment will be due a week from that Tuesday, the 10th of September. But that's going to be on Chapter 10 material, which is where we're headed today. Last time was just an overview, trying to orient you with where we're headed in the semester, where we're going. Now we're going to start in with single phase sinusoidal steady state power, and I might just write that as 1-phi for single phase. We will today look at a single element. That's a passive element that might be a resistor, a capacitor, or an inductor. We'll just develop the equations for a general element, and we'll look at that through the instantaneous power. We'll find average power. We will actually then see that there's other things we need to keep track of, and we will call that reactive power. We'll put those pieces together orthogonally and create complex power. And that's where we will hopefully end today with that particular material. Let's then start Chapter 10, which is power, and in more general sense it's complex power, but we'll see where that's coming from. Let's establish first of all notation or terminology. If this is just a generic element, right now we are not specializing that to be anything, but it's going to be a resistor or an inductor or a capacitor. But we can simply talk about it in a generic sense. Here is our current, I of t, and we will let that current flow into the positive terminal. So the defined current that we've labeled, I of t, would be positive going to the right. That's going into the positive terminal of this generic two-terminal device. This now will give us a positive power using this passive sign convention, meaning power being absorbed by that generic element will be a positive value. If we end up multiplying I and V and it ends up being a positive expression, it may be going up and down, but let's say when it's positive, then it's absorbing power, and that's our sign convention. If it ends up being negative, then that particular element would actually be supplying the power. Is that clear? That's the notation that we're using. Let's now think of, or simply look at, time domain expressions for V and I. We can say here's our maximum value, V max, cosine omega t plus some phase angle. That's supposed to be a lower case v, that's theta sub v, or that v sub m is the maximum amplitude. We could also write that amplitude, and for what we are doing in this class, it will end up, we won't have to chase as many coefficients around if we actually denote these amplitudes in RMS units. So we can relate Vmax and Vrms by this square root of 2 factor, and by keeping track of RMS units, that will clean up our formulas or our expressions. The current has a similar structure. its phase angle we will denote by theta sub I, and likewise it's now this square root of 2 I RMS cosine omega t plus theta sub I. And just to simplify things, we could decide where we draw in the sand or on our paper t equals 0. Let's just define time t equals 0 to be when the current is at its maximum. But we still want to keep track of that current's phase angle. But for now, let's just select, in somewhat of an arbitrary manner, let's just select t equals 0 to be the time is hitting its peak, or when it peaks. And if we keep theta sub I and theta sub v, keep track of those, then what we want to do, or what we can do, is we can say, okay, let's let v of t be this v max cosine of omega t plus theta sub v minus theta sub I, and our current now. So all of the angle is in one of the arguments, or this angular difference, theta sub v minus theta sub I, and I sub t is now this I max cosine of just omega t. Haven't really done anything. I've just drawn in the sand where I'm saying t equals 0 is located. And now I'm interested really in all of this discussion. I'm interested in what's the phase difference between my voltage phasors or the voltage signal's phasor angle and the current phasor angle. I'm interested in their separation. Last time you were okay with me simply saying or defining the instantaneous power. I didn't hear too many revolts on that, and that was just the product in time of voltage and current. That's pretty easy to think about. That's our instantaneous power. In terms of the functional expressions that we've now created, that's just v sub m, I sub m, if we pull all the magnitudes out front. We have cosine omega t plus theta sub v minus theta sub I. And I always run out of room, and I won't really make you too mad. I won't go ahead. I have actually an infinitely wide piece of paper. If I wanted to, I could just keep scrolling to the right. But that might frustrate you if you're taking notes. You're going, how can I keep getting that line longer and longer? So I think you'll know what I'm meaning. I'm going to now multiply that by cosine omega t. Is that clear? So that I don't have this infinitely wide piece of paper. Now, we as engineers like to clean things up or make things a little easier, and trig relationships in the time domain can get kind of messy or tedious just to play with. And so what we like to do is maybe pull out the useful information and not play with time domain expressions. That's why we've created this phasor concept, or these ideas of phasors, where we're simply looking at the magnitude and the angle. Now, what we want to do, though, is we have to multiply a cosine with another cosine, and now we can go back to our trig relationships. Here's sort of an aside. We want to see if we can get some useful information out of this expression for instantaneous power of a generic device. We've just defined voltage and current to give us something to work with. If you are playing along in your textbook, you have actually all these trig identities in Appendix F. And the one that I want is actually number 8. if you're flipping through your textbook tonight or Friday or Saturday, whenever you're studying, whenever you like to study. It's now number 8 in the trig identity, which is Appendix F. What we're wanting to use then is the relationship for this product of cosines. We have the cosine of alpha, cosine of beta, and maybe you have this memorized. Does everybody have that memorized? No? Cosine, 1/2 cosine of the difference of those arguments plus 1/2 the cosine of the sum of those arguments. And if you really wanted to derive this or verify it, you could go back to our buddy, our friend, which is Euler. You could plug in, and if you remember your complex algebra, just plug in cosine of alpha, cosine of beta, multiply it out. Now you just have to remember how to multiply with algebra, and it'll boil down to giving you the right-hand side. That's one way of finding that expression. Now let's use that expression to rewrite this instantaneous power. And now what we're doing is we are saying that this argument might be our alpha, and that argument is our beta. And if we do that, you're going to see that we end up with a bigger piece or a bigger expression for P of t. We're going to get 2 pieces. So now P of t is going to be 1/2 V max I max cosine of alpha minus beta. And what happens when we do that? Alpha minus beta, the omega t terms go away, don't they? So now we have some expression that's not a function of time as our first term. We have 1/2 V max I max cosine of that angular difference, theta sub v minus theta sub I. That's our first piece. And we also have whoops, don't want to do that twice. V max I max over 2 times the cosine of alpha plus beta. Now we've doubled our frequency, haven't we? We now have 2 omega t and that angular difference. So now we have 2 omega t plus theta sub v minus theta sub I. What's interesting now about this expression for our instantaneous power in a generic device is that this piece right here is not a function of time, and it's actually constant. That just depends on the angular separation, and once you have those angles, the cosine of that angle gives you a number. Now you simply have a 1/2 V max I max times that number. This is our part of our instantaneous power that's time varying. And maybe that's a little ornery, so let's just go ahead and Appendix F was so kind to us before. Let's go back there and find the cosine expression for, let's say, cosine of alpha, let me call this alpha 1 plus beta 1, where now I'm going to say this is my alpha 1, and there's beta 1. This now ends up being cosine alpha 1 cosine beta 1 minus sine alpha 1 sine of beta 1. And that, if you're playing along in Appendix F, that's formula number 2. I know you want to know where is all this coming from, right? Maybe, maybe not. Maybe you just accept everything on faith. I don't think that's quite what you want to do. You're developing as an engineer. You need to be able to think through all of this. Now, P of T, our instantaneous power, we're left with what we had to begin with, this constant piece. And now we have 2 more terms added on to that are coming from this cosine of the sum of 2 angles formula. Now we have plus Vm over 2 cosine, and now I'm going to pull the beta 1 out front, theta sub v minus theta sub I, cosine of alpha 1, which was 2 omega t. And I also have this V max I max over 2 sine of theta v minus theta I sine of 2 omega t. And now maybe it's easier to think about mentally what's going on. Now you have a cosine at twice the original frequency, where the frequency was the frequency of oscillation of your voltage and current. And you have minus some number times the sine of that same frequency. And you can sort of mentally picture those. Maybe you can't add them up in your mind, but you can feel what's going on. You have a constant plus some time-varying pieces. And the time-varying pieces are going twice as fast as your original frequency of your voltage and current. And what were those in the United States in the power industry? What's omega, roughly? That's F, right? F is 60. 2 pi 60, you could have answered, which is 377, right? So 377 is the omega that we have agreed to sort of play with. Well, now we're twice that. So double 377, and now we're above 700 in omega, in radians per second. Is that clear? What am I wanting to do? Well, this is kind of ugly. This is what's always going on. Yes. But we can see that we have things happening as a result of this angular separation between our voltage and current. All of those, that difference drives each of these, or weights each of these 3 terms in that expression. If our voltage was aligned with our current, theta sub v and theta sub I would be equal. Then we would have cosine of 0, 1. And what do we have down below? Sine of 0 is 0. Now we have this other piece that's floating around, but maybe we don't want to worry about all of this oscillation. Maybe we just want to know what's the average behavior. What's the average power? This is the instantaneous power. We may want to know what's over time, what's the average power? That's what I want to be charged. So now let's average this. This is P of T, and from that we can actually think about the average, or what we actually call the real. That's another term, so I may use these interchangeably. I may talk about the real power, or I might talk about the average power. It's the same thing, but now let's examine that. So P average, when you average something, you basically integrate it over a period of time, let's just say from 0 to the period, cap t, and we have the instantaneous powers expression P of t dt. But in this particular situation, we know what capital T is, don't we? Capital T is related to our frequency. It's the reciprocal of our F, which is 60. So now capital T is 1 over F, or 1 over 60. We don't really need to know that, but if I now integrate over one period, 2 cycles, which is what I have on the two right-hand terms, what happens when I integrate 2 cycles of a cosine? It sums to 0, doesn't it? I have the same amount of positive area under the curve as I have negative. Likewise for the sine piece. If I integrate 2 cycles of a sine wave over one period, I'm going to get 2 positive humps and 2 negative bumps, and they're going to be equal. So they're going to cancel. If I now average this, what's going to happen? If I average P of t, and what was that first term? So you've just told me, I hope, or you sort of believe, that those last 2 of the 3 terms are vanishing when I average. So I'm going to say, just to sort of remind us, that the cosine 2 omega t and the sine 2 omega t terms integrate to 0. Which means we can sort of neglect those when we put P of t under that integral sign if we wanted to, and now we simply have that first piece, that first term of the 3 terms. And what did we say that first piece was? It was constant, wasn't it? What happens when you integrate a constant? That you wished you would have been given on the final of your Calc 2 exam, huh? Integrate a constant. Really? Is that the final? I can maybe do that. I can now sum up the area under this constant. And how long are we integrating that constant? 1 period. So that's a constant times the period divided by the period. Pretty easy, huh? So what's our average power? P average is now simply going to be 1/2 V max I max, and we can't forget this scaling factor. That's just a number, but it scales our result. Now, as I said before, we might want to clean that up a little bit by not using the max expression for voltage and current, but maybe the RMS, and the V max was the square root of 2 times V RMS. I max was the square root of 2 times I RMS. Square root of 2 times the square root of 2, 2. We're dividing by 2, so we could rewrite this and maybe you don't like red marks on your paper, but I kind of like red marks actually. That's a good thing here. This is a key formula. This is the average power. We simply need to know what's the voltage across our device, what's the current through that device, and what's the relationship on their peaks. And if I know theta V minus theta I can calculate the cosine of that angle. And that will give me the average power. And I also have called this the real power. And in sort of words, this real power is a measure, or it measures the rate of energy consumption used to, let's say, transform from electrical to potentially non-electrical energy. Meaning if it was just a resistor, we'd be heating up that resistor. That's another form of energy, that heat. Maybe we want to convert it into something mechanical or something that's lighting. But that gives us the power that's actually being used, this formula. Vmax, or Vrms, Irms, cosine of theta V minus theta I. Let's now look at this. This was derived, this P of T equation was derived without assuming any kind of element. We didn't assume an R, we didn't assume an L, we didn't assume a C. We just said, here's a V, here's an I, let's just write this formula or expression. We can now specialize this instantaneous power formula for the three different circuit elements that we'll be interested in, R's, L's, and C's, and then see what falls out in terms of real power and what else is happening. Let's now look at these different impedance values for the generic element that we started with. So first, let's start by sort of crawling. That's how you try to start doing things, right? You crawl, then you walk, then you start running. Well, maybe when you were first learning how to walk, you were actually kind of running, but we'll neglect that concept and just say, let's start crawling. And crawling is pretty easy with a resistor. The impedance of a resistor, you've already learned. That's just R. It doesn't depend on frequency. So Z sub R, the impedance of a resistor, is R. And with that information, what do we know about the relationship between the current and the voltage of a resistor? If you looked at those two signals on an oscilloscope in the lab, what would happen to their alignment? Where would their peaks be relative to each other? They're the same, aren't they? We're aligned. So the current and voltage, and we say that that concept is they're in phase, which says then that V sub theta sub V is equal to theta sub I. And if we plug that in now to this red boxed equation, red box, do we have a movie? There's probably a movie of this. It'll be on the D2L website tonight. Okay, you can go play it. And it won't even cost you $1. Okay? And there's not a late fee if you forget to turn it in. Don't play this beyond your own rooms, huh? Or I'll probably get in trouble for some violation by mentioning red box. But we have a red box on our page, right? And some of you are going, what's he talking about? Hopefully you know. Anyway, this is reminding me of a CD that I would stick in, or a DVD that I would put into Redbox. This keeps me honest here. Ooh, really? I better, oh, see, I can't see through the flag. So I have to come over here to see the time, and that sort of delays me. So I better keep on task. Where was I? I went to the red box, right? I went back to the red box, and you better not forget this formula. Since I made such a big deal about it, you now know, oh, red box, VI cosine. So now when you drive by a red box, what are you going to see? This formula, right? Yeah. All right, and I could have just listened to the bell and known what time it was. Wouldn't have to worry about all these clocks and the flag and the Constitution. What's the average power of a resistor? cosine of theta v minus theta I is 1, isn't it? When they're equal. So now we have vi cosine of 0, that's just vi, where we're saying or implying that those had units, RMS units. And what did we say last time? This has units of W, or watts. So now we know a little bit about the average power of a resistor. It's just VI. That's what we did in 220 on the first week, right? We worked with DC units or concepts. Now RMS units are like DC. That's why we converted to RMS in the first place, is so that resistor would give us the same kind of power loss for an RMS unit as a DC unit. All right, so we need to move beyond that. Let's now, and before we go tripping off into L's and C's, their impedance, let's just remind ourselves of and I'm not sure if Dr. Marcelin uses this or not. Does he in 220? Okay, good. So you know Eli the Iceman, but now what we want, and E's are what? Representative of voltage. I is current, and the L and the C is our inductor and capacitor. And this actually gives us a way to keep track of, if I now start saying on the exam, does the current lag the voltage, or does the current lead the voltage? You go, I don't know, Eli the Iceman. So if you just write this down, that will tell you what's happening. Now, you maybe have viewed this by, and I tell students this also, just use Eli to remember the voltage current relationship in the time domain of your inductor and capacitor, meaning you now have V sub L of t is equal to L di sub L dt, and I sub C of t is equal to C dV sub C dt. Those are now the governing relationships, but you also can use this left to right relationship on E and I in the inductor and capacitor equation. If you wanted to know what's the relationship between the current and the voltage in the inductor, you just have to remember Eli. And you see, well, I is behind E in terms of reading from left to right. So I is coming later than E, or voltage. So our current comes after the voltage, and the term that we will use is we will say that the current lags the voltage. Did you learn about leading and lagging in 220? Okay, so this is all review. That's what's happening then in your inductor. Likewise, for the capacitor, in ice, your current comes before the voltage, or the current now leads the voltage in the capacitor C. All right, that's sort of our background, and now we know what we need to know, or what we need to remember as far as leading and lagging. If our current is lagging, then we're dealing with more of an inductive type load. If our current is leading, then our load looks more capacitive. It may not be purely capacitive or purely inductive. It's just more of one than the other later. Right now, let's just look at the specific case where we are looking at the individual parameters. Case 2. Case 1 was the resistor's impedance. What's the formula for the impedance of the inductor? And you told me this last time, so you better not have lost it between Tuesday and Thursday. That's J omega L, isn't it? Or in terms of reactance, we might say X sub L for omega L. And this is our expression for the inductor. Now we want to figure out what is P average for the inductor. Up above, we just said that the current in this inductor lags the voltage, and now we simply need to remember what J looks like in terms of an angle. If we were looking at this in phasor form, we might have V is equal to Z sub L, I sub L, and this is now, let's say, V RMS at an angle of theta sub V is equal to the impedance, J omega L, I RMS at an angle of theta sub I. But this is just the same as the magnitude, omega L, at an angle of, what's the angle of J? And if you forget, simply remember your complex plane. Here's the real part, here's the imaginary part. There's J, and all of our angles in this course and other courses are referenced to this horizontal line to the right. What's this angle? 90 degrees. So J is 90 degrees. So now we know the relationship between the voltage and the current. If we said theta sub V is equal to, well, if we're just adding up phases, if we're just worrying about the phase expression, we now have theta sub V. Phases add, don't they? So now we know that theta sub V is equal to 90 degrees plus theta sub I. But what do we need? We actually wanted theta sub V minus theta sub I in our formula, and we can get that pretty easily with some algebra, which is why you took that in second grade or whenever you get algebra. I don't know, you guys are getting algebra so quick now, then it gets kind of lost by the time you get to this point. Is that correct? Theta sub V minus theta sub I is 90 degrees. All right, now we can plug that into P average. P average was V RMS, I RMS cosine theta sub V minus theta sub I. And we said, let's look at this for the inductor. But now we see that this guy is 90 degrees. So what's the average power or the real power of an inductor? What's cosine of 90? If you had an ideal inductor, which means no parasitics in that inductor, no resistive behavior of that in that inductor would not absorb any power. The real power would be zero. What? I'm confused. So let's think this through here. What happened to our current? Our voltage and current now are 90 degrees apart, aren't they? Well, let's look at this generic instantaneous power formula. We had 1/2 V max I max cosine of the angular difference, so that's what we expected. That's what we said our average power was to begin with, plus 1/2 Vmax Imax cosine of theta sub V minus theta sub I cosine of 2 omega t. And then we had a minus 1/2 Vmax Imax and what does that boil down to then? This vanishes. This vanishes. We're left with just one piece for the instantaneous power in that inductor, and that's minus 1/2 Vmax Imax, sine of 90, 1, and what are we seeing? We now see that the instantaneous power in this inductor is twice the frequency of both the current and the voltage frequency. And P sub L of t in L oscillates. The instantaneous power in that inductor is going up, down, up, down, up, down, up, down, at twice the frequency of our voltage and current. What in the world is going on? Well, when that P sub L of t is positive, so let me sort of say what's going on. When P sub L of t is, let's say, positive, then what we actually have is we have energy in our system being stored in the magnetic field of that inductor when it's positive. So now we have storage of energy, and when it goes negative, it collapses and it gives that energy back to the source. So we're just breathing as an inductor, where our breathing is storing energy in the magnetic field of that inductor. So it's when P sub L of t is positive, we have energy stored in the magnetic field. And when it's negative, it's just releasing that energy back to the source. And we could then say that we have energy delivered back to the source. And this is what the power company gets a little ornery about. They're going, why is this guy breathing? Why is this plant over here, plant not meaning a green leafy thing, but this industrial complex, maybe you're manufacturing something and there's all sorts of machines there. It's going, wow, up, back, over, back, over, back. They want to keep track of that, don't they? They want to charge you for that because you're kind of being a nuisance. Because you're what? You're pulling it, then giving it back. Pulling it, giving it back at twice the frequency of where you started with their currents and voltages. So we need to keep track of that power. Although there's no real power being absorbed, is there, in that inductor? It's just pulling in, pushing it back. Pulling and pushing. We would like to keep track have this energy, since the current, in order for that power, and what do we need for power? Voltage and current. So we have current going back and forth, maybe from the plant to the source. There's transmission lines between that. And we're losing a little bit every time we go back and forth, because there's resistive losses in those transmission lines. The power company, you're not getting the benefit of that, because what you're doing is you're using the real power, and all that reactive power is just floating back and forth. But the power company's sitting here delivering or supplying all of that, and it's losing some in the battle. But it keeps track of what's going on its terminals, and it charges you for what it sees. So we need a way of keeping track of that. Because if you become employed by the power company, you're going to be the one wanting to benefit from that, right? And did everybody, I don't know if it happened today, but yesterday, the power company was on the mall. That could have been one of your current events. I was just walking down the mall. Would you like some light bulbs? Sure. So I have some high efficiency light bulbs. It's only going to cost me $1.56 a year to power that 60 watt, effectively 60 watt light bulb. Current event, right? And I got 4 of those in a box. They're small, they're miniature. I need to get back. I'm getting lost between red box and light bulbs. We have current though, don't we? What do I have? Current, oh, I didn't even finish that sentence. Since the current is actually flowing in the lines. And the way that we are going to keep track of that, we can't call it real power, can we? Because real power is 0. Whoops, let me change colors here. Let's call it reactive power. And it's actually needs to be orthogonal to the real power. And the real power was related to the cosine of the angle between the voltage and current. And if we want to be orthogonal to cosine, what function do we want to use? Sine. So now the reactive power, which we're calling Q, we had real power, we'll call that P. So now we have P's and Q's, and don't get me started on a joke for P's and Q's. Okay, but we now have Q, and we're going to call this Q V RMS, I RMS, sine theta sub V minus theta sub I. And a lot of times we will just abbreviate that. Theta sub V minus theta sub I is really just the angle of the impedance, and we might just simplify that and call that theta in future formulas or formulations of these problems or working these problems. And the units, VARs, that's volt amperes reactive. And wow, you know what I think I did? No, maybe not. Oh, I did. Shoot. Well, I forgot something. I got so worked up on that red box before. But let's go on right now, and we'll call this, or define, a reactive factor, which is just this number, sine of theta sub V minus theta sub I, which we will call RF. Now, that will make more sense if I would have already defined our power factor, which is actually the ratio of P average over V RMS I RMS. But if you go back to the P average formula, what's that ratio? So somebody might say, what's the PF of that system? What's the power factor? It's going to be the cosine of your impedance angle, essentially. But this is also, since we're introducing all these terms, this product is the apparent power, and that's what the power company knows it's having to produce. Its maximum voltage and its current maximum may be quite a bit bigger than what you're actually seeing at your plant where you're using the power. So this apparent power and what you're actually using, the real power, we like to keep track of that ratio. And if the ratio gets, let's say, below 0.8, if you're using 80% of the power that the power company is apparently supplying, then you may have a surcharge on your bill. If you have a residential power bill, you probably don't see a power factor on it, do you? You just see kilowatt hours, because your house doesn't look that much like an inductor or a capacitor. Your AC unit would present itself to look somewhat inductive in nature, but it's not going to drop this power factor much below 1. But when you do in a big industrial facility, you'll get charged for that. There will be a surcharge because your power factor is too small. And that's the ratio of what the real power is that you're able to use versus the apparent power that the company is having to produce to supply you. And that's because you've got these big machines that are inductive in nature operating. And they look like inductors, effectively. All right, so now we have power factor and reactive factor. And we can now look at what happens in an inductive circuit relative to the current and the voltage. I'm continuing to harp on this because I don't want you to miss it on the exam or the final. The current lags the voltage in an inductive load. And we've just seen that in our particular case, so here I'm generalizing this idea. Maybe we don't have a purely inductive load. Maybe it's not all just an inductor. Maybe we have a resistor and an inductor. If that's the case, then this won't quite be 90 degrees, will it? But the current will still lag the voltage. So the angle of the current is going to be smaller or less than the angle of the voltage. And if that's the case, then we can say that this angle theta has what sign? It's going to be positive, isn't it? If this angle is positive and we're taking the sine of a positive angle, what do we end up with for Q, for our reactive power, magnitude, or sign? SIGN. It's positive, isn't it? So with an inductive-like load, Q, our reactive power, better be positive. And we will say that we now have a lagging power factor. And why do we need that lagging? Because if we take the cosine of an angle, that angle might be positive or negative. The cosine doesn't care, does it? So it kind of loses track of that angle. It gives us a number, but then we need to tell us, was that angle positive or negative? If it was positive, it's going to be a lagging power factor. It's going to be, let's say, 0.7 lagging. We have to give both pieces, the numerical value and the adjective, lagging. And I think you can anticipate what's going to happen with the capacitor. It's going to be a leading power factor, and Q is going to be negative. So that's where we're headed. Let's now then move to the capacitor. The impedance of a capacitor, 1 over j omega c. If we pull that j upstairs or multiply by 1, which is j over j squared is minus 1, and now we have minus j times 1 over omega c, or minus j omega x sub c, and this is for a capacitor. And based on our Eli the Iceman, we now need to know the ice part. We now know that the current leads the voltage. And if we were looking at our expression before, if we had V sub C is equal to Z sub C, I sub C, now we have, if we just looked at the phase of that expression, we would have theta sub V is equal to, what's the angle of our capacitor? There's a J there, that gives us 90 degrees. But the minus sign flips us down, doesn't it? It goes 180 degrees. So this is minus 90 degrees. This now says that we have minus 90 degrees plus theta sub I. Or theta sub V minus theta sub I is equal to minus 90 degrees. Again, we can compute the average power for a capacitor, but you should already know what that's going to be. Zero watts. In this case, the real power, the instantaneous power of that capacitor, it too oscillates back and forth at twice the frequency. And we can do the same thought experiment, but now we don't have a magnetic field, we have an electric field, don't we, with a capacitor. So now we're breathing with our capacitor. We're taking in or energizing the electric field, and then we collapse it. We store energy in the electric field, and then we give it back. So when P sub C of t is positive, that now says that we have energy stored in the electric field associated with our capacitor. And when P sub C of t is negative, now that energy is delivered back to the source. Again, we know for a capacitive circuit, so if we talk now in a little bit more general terms, if we had a resistor and a capacitor combined into a circuit, we would have a circuit that looks somewhat capacitive. We would still have our current leading the voltage. And if we looked at this difference, theta sub V minus theta sub I, we would get an angle theta. But now, if theta sub I is leading theta sub I, we could think of that as being bigger than theta sub V. We're taking a bigger number from a smaller number. This is now negative. And this now gives us a leading power factor. Now we've looked at the individual pieces. We've looked at R's, L's, and C's and their impedances and what that translates into relative to real power and reactive power. Now if we combine those pieces, we are going into a circuit. We now have complex impedances in this circuit. That's going to then translate into complex power. Not just real power. Now we want to combine the real part and the reactive part to get a complex power. And that's what we'll be playing with now. And that complex power we are going to label as S. That's supposed to be an S. And that's P, and orthogonal to that is Q. Here is our complex power. P is our real power or average power. And Q is our reactive power. In terms of our formulas, S is now V RMS I RMS cosine theta sub V minus theta sub I plus J V RMS I RMS sine theta sub V minus theta sub I. But hopefully you see Euler. What? Cosine x plus j sine x. That should be talking to you in terms of, oh, that's this e to the jx, isn't it? So we could write this complex power S by invoking Euler as V RMS, I RMS. Let's factor those two constants out, or the product of those two out. And now we have cosine x plus j sine x. That's just e jx. But we can sort of play with our exponents a little bit. We can now say, you know what? Let's combine the voltage pieces. That's just V RMS e to the j theta sub v. And let's combine our current pieces. That's I RMS e to the minus j theta sub I. But again, this is our complex power, and sometimes I'll write a bar over it, sometimes I won't, but S bar means it's complex. This is our voltage phasor, isn't it? So we could say that this is V RMS phasor. What is this piece? It's almost the current phasor. Pardon? That's the complex conjugate, isn't it, of our current phasor. So now we have I RMS phasor complex conjugate. And this also needs a box. And maybe we'll be getting something from the black box at some time. Probably not a DVD, right? But this has units of what? VA, volt amperes. And now, what are some different ways of thinking about this complex power? You're probably very visual, and that if I did the entire class on your passport assignment and I looked at the number on that spectrum where one of the sides is visual, I think this class would probably average on the visual side versus its other form of learning styles. So give me a picture, right? And that picture that we can think of when we're dealing with complex power is not the Bermuda Triangle, it's the complex power triangle. And here it is. We now have this complex power S. On the horizontal axis, we have our real power, P. On the vertical axis is our reactive power, Q. And if Q is positive, then we have a more inductive load than we have capacitive load. And S is also this phasor. I should put an arrow on it. And these are related by this angle theta, which is theta sub V minus theta sub I. If Q went down, I got too excited about the boxes. What on earth? Oh, that looks pretty. Hello. It's on strike with the, I shouldn't have been so impatient. And now I've probably lost everything above that triangle, but you were taking notes, I hope. What I was trying to do, and who knows if it's even going to come back to life, we'll see. Let's now look at some of these expressions. The average power, P, in terms of this complex power triangle, that's now the length of our complex power, which is really the apparent power, that's the magnitude of S, times the cosine of theta, that's our real power. S is this where the magnitude of S is actually VRMS, IRMS at an angle of theta. This is our apparent power. S is our complex power. And Q is the apparent power. Is the reactive power. I'm so frustrated with was it when I was coming into work today that they were talking about people wanting their car to just be an extension of them, sort of like their phone, that the car starts to learn their mannerisms and where they're going, what they like to listen to. I had no idea where I was going with that. Oh, now it's back. They said that your car, even though you might like it to be like your phone or the computer, you probably don't want to be flying down the interstate and it have to reboot. Right? I mean, with a phone, you can kind of accept it crashing. But you don't want your car to crash in terms of being able to drive it. So now as engineers, if you're trying to put all of this intelligence into a vehicle, You need to make sure that you don't have to always be pushing this reset button on your vehicle, because you might be in a busy intersection. Oh, I need to reset. I need to reboot. That may not work, huh, with a vehicle. Something to keep in mind. So that's what I was thinking about. This silly thing had to reboot, sort of, right? Kind of had to take a break. We were using too much power. Maybe it didn't like the complex power. And it said, wait a minute, I need to take a break. But what is complex power? It's just a combination of real power and reactive power. And that keeps track of what your loads look like. If we now looked at a problem, so here's your quiz. Now you guys want to reboot, right? I'm pointing at the doors. You won't hear that on the audio, will you? Here would be a quiz. Suppose that I said, okay, here is our circuit from before. Except now I'll go ahead and give you these impedance values, and I will represent the source as an RMS voltage, and here is our load voltage. What if I ask you, for example, whoops, they're wanting to restart, not reboot, right? Suppose I ask you to find the complex power supplied by the source. Now, do you see that I can offer you all sorts of questions just by sketching this particular circuit? We could view this circuit as if this piece is the load. This piece could represent our transmission line. And now we are supplying power to this load through this transmission line. And I might just say that's line. I may forget transmission. I may just say, okay, what's the loss in the line? What's the line loss? The power loss. Or what's the complex power at the load? What's the power factor of the load? What's the power factor seen by the source? But if I say find the complex, what am I writing? Man, I need to reboot. Find the complex power supplied by the source. Find the complex. So I can find anything that's complex, right? All you have to do is recycle some of these notes, and that could be complex, right? And just hand that in. But find the complex power supplied by the source. Now we could find what would be a strategy for doing that. There's many different approaches. But now we're asking for the capital S, which is a complex quantity. If we could find the current that source is supplying, then we would just have to do what to get the complex power of the source? We have the voltage. What do we do with the current? We need to take the complex conjugate of the current, don't we? And then just multiply them. And if they're in polar form, that's pretty easy. Multiply their magnitudes and add their angles. And then if we wanted to put that into a rectangular form, the real part of that answer would be our real power. The imaginary piece of that complex number would be our reactive power, and we would have our answer. What we need to do then is find I that's supplied by the source. And we'll pick up at that point or somewhere on Tuesday. Enjoy your weekend.